This is Jack Jackson. We're back with our third and final video of these review exercises over Unit 2B. Following this video, there's another older video that I have of some earlier review exercises. In that video, you can see me actually pull some problems up from a software called My Labs or My Stat Lab that I'd used in the past. And so you can see me work those out there as well. But to finish up these exercises, this is 11 through 15 from the review exercises at the end of our slides. So, as before, I'll show you a problem, ask you to pause, you work it, and then we'll come back and I'll work the answer. So for number 11, suppose that there are 35 students in a particular section of Probability and Statistics 1, and 70% of them approve of a ban on assault rifles. If we take a random sample of 10 of these students, then compute the following probabilities in decimal form, rounded to 4 decimal places. Find the probability that at least 50% of the students sampled above approve of the ban. And B, find the probability that between 50% and 80% inclusive of the students who sampled approve of the ban. Press pause now. All right, here's a solution. First of all, what kind of distribution is this? Well, we have a finite population of 30 students. We're going to choose a sample of 10 of them and count the number of successes being the number that approve of the ban on assault rifles. So A is the probability that at least 50% of them approve of the ban. Well, this is a hypergeometric situation, right? We have a finite sample size. We're sampling without replacing them. We are going to have 10 different students. We're not going to have the same student twice or more than that in this sample. So the probability that at least 50% of the students approve the ban, but it is a distribution of proportions. Notice that 50%, at least 50%. So p hat, the probability, the proportion of successes in the sample is p hat, and it needs to be at 50% or bigger. What we do is convert that to the corresponding x's. Well, 50% of 10, okay, 50% of what? 50% of what's in the sample. There are 10 in the sample, so 50% of 10, that's 5. So 5 or higher, so that'd be between 5 and 6. All right, so we just run our program, hypergeometric CDF, HGO CDF. Total population size is 30. The number of successes in the population is, oh, we need to figure that out too, right? 70% of 30 is 21. That's got to be a whole number. If it's not, round it off. Okay, so that's 21. The sample size is 10. And we're going to go from a lower of 5 to an upper of 10. And that probability is 0.9816. It gives you the number twice because it's trying to make 1 into an exact fraction form. That rarely happens, but sometimes it does. The probability that is between 50% and 80% inclusive, okay, well, 50% of 10 is 5 and 80% of 10 is 8, so it's between 8 and 5. Then the lower is 5, the upper is 8. That's the probability over here. So 5 to 10, the probability is 0.9816, and the probability from 5 to 8 was 0.8818, rounded to 4 decimal places. And it's just hypergeometric CDF. You got to remember the order. It's the same as the order in the program here. Population size, number of successes in the population, sample size, number of successes in the sample lower, and the number of successes in the sample upper for that interval. All right, here's another proportion one. Suppose that 80% of all statistics students completed all their homework sets with at least 90% correct. If we take a random sample of 10 of these students, then compute the following probabilities in decimal form rounded to 4 decimal places. What is the probability that the sample will contain at least 6 students who completed all their homework with at least 90% correct? And what's the probability that the sample will contain between 3 and 7 inclusive students who completed all their homework with at least 90% correct? Press pause. Come back when you're ready. Press pause now. Well, once again, it is actually hypergeometric again, right? Because we know we're not going to select the same student twice. So it's selected without replacement. Unfortunately, I don't see anywhere on here where we know the actual population size. So it's not possible for us to compute a hypergeometric probability. Now, the best we can do is approximate that with the binomials, and that's what we're going to do. So if we assume that all statistics students, maybe that's all statistics students anywhere, that's a big number. So this is a big population size, so a binomial distribution is still a pretty accurate approximation of this hypergeometric situation. So it's just a binomial that we're going to use. The probability that the sample will contain at least 6 students, that's 6 or higher, that'll be 1 minus the binomial CDF. The sample size is 10. The probability of success is 0.8 every time. And then 5. Notice the 90% really doesn't come into it. That's just our cutoff to decide if it's a success or not. And that turns out to be 0.9672. And then between 3 and 7 inclusive, binomial CDF, again, 10.8. We start with the 7, and then we go minus the binomial CDF 10.8, 2. So notice we're keeping up to 7 and then taking away anything below 3, so that would be from 2 down, so hence the 2. It works a little bit more easily actually on the TI Inspire. It works kind of like the hypergeometric program does. You give it a lower and an upper. So the binomial, let's see, between at least 6 would be from 6 up to 10, because there are only 10. 10's the most you could get there. And then between 3 and 7, just give it 3 and 7. Of course, you still give it N and P first. Same probabilities there. All right, here's another one for you. We know that 60% of Americans think that apple pie is their favorite kind of pie. At least 90% of all samples of size 25 from this population will have more than how many people who have apple pie as their favorite kind of pie. See if you can think about this one and come back when you're ready. Press pause now. Well, this is actually an inverse probability question concerning proportions based on a binomial distribution. And so maybe your inverse binomial is not built into your calculator, but we have a program for that, or I told you how to make a function for the TI Inspire, at least the CAS version here. So what this program is going to do, it's going to produce a portion of the PDF table, a portion of the CDF table for a binomial. So you run this program. Let's look at the TI-84 version first. You run this program called inverse binom. Okay. He asks for the sample size, which is 25. Samples of size 25. The probability of success each time is 0.6. Okay. And then the cumulative probability is 0.1. So at least 90% will be more than that. So that means 10% less. So you put 0.1 below. Okay. And then what it will do, it will produce a portion of the table. So here are the X values, 10, 11, and 12. It's just a portion of the CDF. The CDF table really has going from 0 to 25, so it's a big table. Well, this will produce 3 lines from that table. These are the X's, 10, 11, 12. Here are the corresponding P hats, the proportions, 0.5, 0.44, and 0.48. And here are the probabilities, the cumulative probabilities, 0.03 something, 0.0778, and 0.15376. Okay, it produces them in a little matrix here. Okay, so what are we looking for? We're looking for how many people, let's see, at least 90% of all samples of size will have more, sample size 25 from this population will have more than how many people? Okay, the people is over here in the x. We're looking for that. And we want this to be at least 90% above this. So you really want 1 minus these CDFs. So this would be 0.96 here. Okay. This would be 0.93. This would be 0.85. So we're looking for the highest K value with the cumulative probability not going over 0.1. So the answer we're looking for is 11. Okay. So 11 is the one where it's not going over that. So actually it turns out that about 92%, if you do 1 minus the 0.07788, that's about 92% of the samples will have more than 11 people. 11 or more. Well, no, I'm sorry. More than 11, right? So 11 or less is about 0.08, and so then more than 11 would be about 92%. But if we went down to 10, it would be, it'd be too big. It'd be 0.97. And if we go up to 12, it would be too small, 0.85. Okay, and here's the inverse binom program. Again, you give an n, p, and the cumulative probability, the probability to the left, and it produces a portion of the table there. And you can, again, it's basically the same numbers, just more digits shown. You can pick out the one that you need, and we need 11. And of course, it turns out about 85% of the samples will have more than 12 people. All right, how about another one here? We know that 40% of a fraternity of 25 members are STEM majors. The lowest 20% of all samples of size 6 from this population will have how many people or fewer who are STEM majors? Think about this one. Come back when you're ready. Press pause now. Well, this is another inverse probability problem, right? We want to know how many people, and we know the cumulative probability, right? So, but this one we know the finite population size is 25. So this one is a hypergeometric, whereas the last one we didn't know the population size. This one over here, so we had to use a binomial. So we have a program for that too, right? It's inverse HGO. Run that program. The population size, the total is 25. The number of successes in the population is 10. The sample size is 6. The cumulative probability is 0.2, so the lowest 20%. And it produces a piece of the table. You can scroll left and right within this to see it. Well, it's stored as A, so it tells you that. So after you get out, if you can't see everything, just type A, which you get from matrix, and it'll be the number 1. So just matrix enter. And then you'll get this matrix here, and you can scroll left and right within it. So first of all, we're looking at the probabilities. Well, what do we want? We want the probability that x is less than or equal to k to be less than 0.2. Okay, so look at what we've got. It gives us the portion of the table. Well, 0 is 0. 1 is well, 0 to that many decimal places anyway. 1 is 0.16 repeating, say 0.17. 2 is about 0.33. So where is the, looking for where it marks off the bottom 20%. Okay, and that's going to be right about here, which is more around 19.8%. We'll have 1 or fewer. And so what number we're looking for is the x value there, 1. So we're looking for the highest x value that it doesn't go over 20%, doesn't go over 0.2 over here. So there's another inverse probability problem. Okay, and the last one in this little set, let the random variables x and y be independent. Complete the following table of parameters. So we have random variables x and y. The means are 300 and 250 respectively, and the variance of x is 25 and the variance of y is 49. We want to find their standard deviations, and then look at some new random variables, 2x, y plus 3, and x plus y, and find their mean, variance, and standard deviation. See if you can do this one and come back when you're ready. Press pause now. Well, first of all, the relationship between variance and standard deviation is the standard deviation is the square root of the variance. So square root of 25 is 5, square root of 49 is 7. When you multiply something by 2, you double the mean. So 2 times 300 is 600. You also double the, whatever that 2 is, do the absolute value of that, multiply by the standard deviation will give you a new standard deviation, was 10. Square that, you get 100 here. So you end up multiplying the variance by that 2 squared. Or just find the standard deviation and square it. Now y plus 3, shifting, so notice that multiplying, let's go back, is going to multiply both the mean and the standard deviation. But when you add 3, it's going to shift the mean by that much, so 253 for y, there's y, 250, add 3, 253. But it doesn't change the variance, and that's a typo. Let me fix that. So, of course, that's the same, but the same as y, not x. So it doesn't change the variance or standard deviation. Notice just shifting this moves the location of it, moves the center, but it doesn't change the overall shape. So the spread doesn't change any when you add a constant or subtract a constant from a variable. Now, when you add two random variables, their means just add up. So that's pretty easy. 300 plus 250 is 550. And their variances add up. 25 plus 49 is 74. The square root of 74 is approximately 8.6023. So find their variances add up. Now, if you weren't told the variances and you just had the standard deviations, notice you can't just add those up, right? It's bigger than either one, but not as big as the two of them added together. So you first square both of those to get the variances, add those up for the variance, and then square root that to get the standard deviation there. Okay, I think that brings us to an end on these review exercises. Again, this should give you a good idea what to expect on the practice test on my class. And if you notice, a lot of this is about being sure you can run your calculator programs. You have to identify the right distribution, run the correct program, put in the correct values, and then interpret your answers. The calculator, however, will do the grunt work. Again, there's another video after this with some more programs, more review exercises, but they're not in the slideshow. All right, happy studying.